Okay, we resume. We look into the uncertainty, probability, and data visualization. So, first we look into uncertainty. Is basically the limit. So it is basically defined as measuring error exceeds some specific value. Uh, so it is like a bound of error. It's a limit of the measurement. It's not the error itself, but uncertainty basically tells us the bound of error, okay, or bound on the true value, okay, so which tell us the limit of the true value based on the measured value minus the bound. Okay, so it basically shows us the limit of our measurement in terms of the ideal. This figure shows the ideal device based and then versus the actual. So uncertainty tell us the limit, okay, the interval so of our measurement. It's not the error itself, but it shows us the level of confidence of our measurement. So first we look into the uncertainty propagation. So in our measurement, the usually involves calculation of several quantities. So in one set of measurement, so maybe it want a combination of multiple quantities. Uh, as for example, is a summation or multiplication or division of several quantities. Okay, so each measurement uh, or each quantities have their uncertainty. So we need to include the uncertainty for each quantity into our measurement. So this is called as the propagation of uncertainty. Uh, okay, for example, in Y, where we have calculated parameter depend on few variables or few measured values, independent values. So each independent value, they have their own uncertainty. So we need to include that uncertainty to get the calculated result uncertainty. So the first step, okay, in calculating the propagation uncertainty is to differentiate every independent value, okay, differentiate to the differentiating the independent value and then multiply with the uncertainty, okay, and then we can calculate the maximum uncertainty for the calculated value based on this formula, okay, by summing, first differentiating each independent variables, okay, and then multiply the variable, the independent variable with its uncertainty, and finally we sum all the worst case possible maximum uncertainty. Or the uncertainty is calculated in RMS uncertainty. Okay, so we look into example here. So in this case, VT, okay, VT, the calculated measurement, okay, VT is equals, okay, to V out exponent negative T over RC. So that's actually what's the actual uh, uh, formula looks like. So VT depend on a few independent parameters here, where it depends on 4 independent parameter. Okay, one is VO, number 2 is T, number 3 is R, and number 4 is C. So there are 4 independent variables. So Vt is the function of Vo, T, R, and C, and the formula is given by this equation. And each of the independent variable, it has its nominal value and its uncertainty. Okay, so this is the nominal value. So those are the nominal values. Nominal values. Okay. And this is the uncertainty level. Okay. In the form of absolute error lah, the uncertainty level. So we can, this is the U U V O. So and this is the uncertainty level for the T U T, and this is U R, and this is U C, the uncertainty. Okay, and there's the nominal value. Okay, for example, for V out is 10 volts. Okay, the nominal value, and the uncertainty is 0.5 volt. So we need to find the what is the maximum uncertainty. Okay, maximum uncertainty is this formula lah. Okay, so the first step is to find the nominal value of V, the calculated value. So we need to find what is V equivalent to V out exponent negative T over RC. Okay. Find the nominal value because we have know all the nominal value for the independent variables. So we need to know the nominal value for the calculated measurement, or the V or the calculated variable here. So so we find that, okay, so V out, okay, we plug in all the values. So we get 10 exponent negative 1, okay, equivalent to 3.68 volts. So that's the nominal value. Okay, we hold that nominal value. Okay. So second step, we derive the independent value. Okay, derive. So we need to do each part. Okay. Okay, so so it means that For example, so the main equation is V equivalent to V out exponent negative T over RC. So we need to differentiate this equation, differentiate against every uh, independent variable, and then multiply the uncertainty. Okay, so we need to do that for four times lah. Okay, need to find dv over dv out, and then multiply with uncertainty. Then you have to find the term here. We call this as okay, let's say this is term 1, term 2, terms 3, and term 4. So we need to find each term result, okay, or equation. Okay, the first term here, okay, dv out over dvo. So we get this result. So how do we get this? Okay, so differentiate v out exponent negative t over rc over dvo for this first term. Okay, so we differentiate v here to dv out. So that's why we get exponent negative t over rc. Okay, and then we plug in the value exponent, the nominal value of trc. So we get negative 1. So and then we get the first term value is 0.368 volt per volt. Okay, so that's the first term, okay, of the result for the first term. Okay, and then the second one. So the second one, second term, okay, dv over dt. Okay, so you see first term is of dv out, then dvo, and then dvt and dvr dvc. Okay, this the second term is dv over dt, okay, which v out exponent negative t over rc over dt. So we can bring v dependent variable vo out and d exponent negative t over rc over dt. Okay, so we need to differentiate this exponent term. So we know that if let's say y equivalent to exponent negative x, so if dy over dx is equivalent to dy over dx is equivalent to exponent negative x, okay, multiply with the uh, d negative x over dx. So you get exponent negative x multiply with negative 1, right? Okay. Okay, so so you check back the concept of uh, derivation of exponent term. Okay. So the product for the second term, d v over dt, we get v out multiply with exponent negative t over rc multiply with exponent negative 1 over rc. Not exponent, sorry. Oh, multiply with negative 1 over rc. Okay. So we plug in all the nominal value. So we get for the second term is negative 3.679 volt per second. Then we will repeat for the third term. So find the for the third term, find the product, okay, of derivation for d over dr. Okay. So you see carefully the result. Okay. Yeah. So here should the output is equal to v out exponent the result of the derivation of dv over dr negative t over rc multiply with the negative t over c multiply with negative 1 over r square. Okay. Then we get the insert all the nominal value. Okay, we get this the nominal value. So plug insert all the nominal value for the independent variables. So we get this value for the third term of dv over dr, and okay, repeat finally for dv over dc. Okay, you get this term. Then we have got all the term. Okay, so to find the maximum uncertainty. Okay, so basically absolute value the dv over dv out multiply with this duvo, the uncertainty. Okay, plus dv over dt multiply the uncertainty of t plus dv over dr multiply with the uncertainty of r plus the result of dv or dc multiply with the uncertainty of c. Okay, this the uvo is the uncertainty lah we got from the first first place here. Okay, uv out, ut, ur, and uc. Okay, and we have determined the value for each partial derivation. So finally, okay, we get the maximum uncertainty value is 1.14. So we can write u, okay, then with the nominal value plus minus the uncertainty of uv. So this is the uv it will become equivalent to 3.68 plus minus 1.14 volt. So that's how we determine the uncertainty of our calculated measurement or value, calculated variable value, based on the independent value and its uncertainties. Okay. Okay, so in this example, so it's much straight question. So we have R equal to R 0 naught 1 plus alpha t minus 20. Okay, and see R naught is 6 ohm plus minus 0.3%. Okay, where the resistance at 20. Alpha here, here is written as A. Okay, so A is equivalent to alpha. Okay, alpha is in 0.04 negative 1 over C plus minus 1%. And the temperature wire T is 30 plus minus 1%. Okay, so this T is okay. The answer T is given in absolute value, but RO and alpha, the value is given in the uncertainty is in percentage. So we need to convert that into absolute uncertainty, okay, for R naught and alpha. So here is stated that 0.3% from the nominal value. So to get the value in the absolute uncertainty, so what we need to do is to 0.3%, okay, this 0.3% multiply with the nominal value. So we get 1.8, 0.018, isn't it? Let me verify. So the absolute value in the absolute value of the uncertainty is plus minus 0.018. So for R naught, so R0, we write is like 6 plus minus 0.018 ohm. So we need to convert into the absolute value first. Similar to this, so alpha, okay, convert, this is in percentage, need convert to absolute. So 1% multiply with the nominal value. Oh, So we get that alpha is equivalent to 0.04 plus minus 0.0004. Okay, C -1. So now you have convert all the values just into a consistent form. The uncertainty in absolute. Then you can calculate the resistance of the wire and its RMS. Okay, RMS uncertainty. Okay, is basically this formula. Okay, whereas you square first and then you sum the value. Okay, then the answer. Okay, you should get the absolute uncertainty. You should get 1 plus minus 0.0305, or in percentage is 0.00305 over the maximum value multiply with 100. Okay, you get 0.49. Yeah, in percentage, so you get 0.9%. So I have convert, okay, the uh, uncertainty in percentage to absolute value. So so you can verify, okay, the answers. Okay, find the nominal value and then the maximum the RMS uncertainty. Okay. Uh, this is another example. I think we will come back to this, but we need to go for the next. The probability. In this case, I will skip. I will not cover. I want to skip to Chopnet criteria. Okay, Chopnet criteria is a process where we use to basically skim our result. In some process we may have a lot of data, set of data. So Chopnet criteria is one way how we find the outliers or find the signal not uh, basically not coming uh, not a part of the actual set of data. So we need to find the dodgy data, and then we want to remove the data. So this method is there are two methods to find the data. First, by find the probability less than 0.5, or by using Chopnet criteria. But I will skip this one, the probability method, but I will go to the Chopnet, okay, criteria. Okay, so to find in the Chopnet criteria, we have to calculate two basic value of mean and standard deviation. Okay, and then we will look into the normal distribution function and then multiply by the number with point taken and see whether the result is less than 0.5. So if that specific data point, the result is less than 0.5, so that data, okay, we can omit, okay, we can remove, and then we calculate the new and standard deviation. Okay, we will look into that step by step. Okay, let look at this example. Okay, we have 6 set of data. 1, 2, 3, 4, 5, 6. 6 of set of data. Okay, and first we find the mean value of the data. Okay, the mean value is basically we sum of the data 100. Okay, divide by 6. So we get 16.67. Okay. Next, we want to calculate the standard deviation. So to calculate the standard deviation, first we need to find the absolute offset at each point, D. So D I is basically the data set, the actual data set minus, let's say the data set is X minus the data set minus the mean value. Okay, for example here, I put here. So A is the data set value 9 minus the mean value, so XM minus 16.67. Okay, so they get 7.67. And then the next B, okay, B is the data set 10, okay, absolute offset minus the mean value, which is 16.67, which the value is 6.67 and so on. Okay, we get the offset. Then we square the offset. After we square off the offset, so we find the standard deviation. Standard deviation is the sum of the square offset divide by the number of set data minus 1. Okay, minus 1. Okay, if the n is less than 30, so we use n minus 1. If the n data set is more than the 30, we use n. So in this case, we use n minus 1. So the standard deviation, and then square root. No. Okay, square root here. So the standard deviation for this set of data is 16.34. Okay, so we get that this this is a example, but this skip this one. Okay, the first method is I think I should explain you about the second method. Sorry, skip this first method. The first method actually based on the probability. So I skip that part. I want to focus on the second method. Okay, the second method using the Chopnet table. Okay, first calculate the mean and standard deviation. So we have looked into that mean, and then we calculate this ratio, the ratio of the deviation or the offset over the uh, standard deviation. Okay, the standard deviation, and compare uh, it with that the Chopnet criteria table. Okay, and then we recalculate the when we remove the data, we recalculate the standard mean and standard deviation. Okay, so this is the table. Okay, the table shows us the maximum deviation to standard uh, deviation ratio. Okay, so let's say in our case, okay, we have six data set. So this is supposed to be the value, the maximum value. So at any data point, if the value is more than this value, so we omit or we remove the data set. Okay. So again, the process, okay, we calculate first. We calculate the standard deviation with six number. Okay, 1, 2, 3, 4, 5, 6. Okay, six data set. So the data is 9, 10, 10, 10, 11, and 50. Okay. Then we calculate the standard deviation, mean and standard deviation. So the mean is 16.67 and the standard deviation for 6 data set is 16.34. So we have discussed how we get, okay, the standard deviation, and we add another column here on the right hand side. The basically the deviation or the offset divide by the divide by standard deviation value. Okay, for each data point. For example, here A, here, how do we get it? Is the deviation value is A di over sigma is equivalent to 7. Okay, here 0.67, the deviation value or the offset value, divide by the calculated standard deviation, which is 16.34. Okay, so that we get 0.47. So we repeat for the second data point. Okay, the offset or the deviation divided by the standard deviation. Okay, so we repeat for every data point. So I'm gonna fill a value on the right hand side of the column here. All right, so we compare all this value on this column. So we know, see, our data set is 6. Okay, our data set is 6. So the ratio of the offset to the standard deviation according to the Chopnet criteria must not be over than 1.73. Okay, so in this example, 50, the 6 data point here, the offset to standard deviation ratio is 2.04, which is more than the value shown in the Chopnet criteria table. So as we can observe, the data with value 50 has exceeded the value in Chopnet table, so we omit or discard. Okay, discard the value. Then when we discard the value, we repeat, recalculate the mean and standard deviation. Okay, so we get that the mean now is 10, and then the standard deviation is 0.7. Okay, so standard deviation is 0.7, which means that the data set is much better nah, if we have smaller standard deviation. Okay, and this least square method basically is a method where it is used to determine the best fit for our linear equation. So if we have a set of data, okay, x on xy, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9 set of data. Based on this 9 set of data, we can determine the equation y m x plus b. So what we want to determine is what is the value of m, what is the value of b. Okay, so the least square method can be used to determine what is the value of the slope m and also what is the value of b. Okay, just keep to the final equation here. So to determine the m value, so n sum of x data point multiply the y data point minus sum of x multiply with sum of y and divide by n multiply with square. So this is the equation. Okay. So I think I'll show you an example of how we can use this data in Excel, because we can compare. Hang on.
Okay, so let's say we have 6 sets of data, X versus Y here. um, so we want to determine the equation, the linear equation, and so we can estimate the slope M and the interception on the y-axis based on this equation. So we can find the value based on this equation. Okay, so we can x square y square x square. Okay, so we find all the value here. Y square. Okay, so this is the value of y square. Okay, and what's next? X multiply with y. So that's here multiply with okay. So that's the value. N is basically 6. Okay. Okay. So we need to find the sum value. Okay. Sum value. This is the sum value. Sum value. This is the sum value. This is the sum value. And this is the sum value. Okay. So right, so this is the sum of x, okay, and this is the sum of y. This is the sum of x square. This is the sum of y square. And this is the sum of x multiplied with y. Okay, is there else? Oh, okay. Sum of x square. Okay. So and n is the number. N is the number of points 6. So to find m, okay, n is 6 multiply with sum of x y here 9.229 minus sum of x here 34.1 multiply with sum of y 13.7. You divide by 6 multiply with sum of x square x square here 2.6507 multiply with the sum of x square. Hang on. No, this is square of sum x, or 34.1 square. Okay. So what you can do is just write the let's find the answer. Write the big divide. Okay, and the top is n6 multiply with sum of xy f10 minus with sum of x is p10 and sum of y is c10. They divide by 6 multiply 6 multiply the sum of x square here minus sum of x square here but square. Oh, so the missing was, what am I missing here? Okay. Which is y square. Maybe I have to put
Doctor, maybe at the 6 times F10. Is that the problem? 6 times F10, maybe you need to put.
okay. 6. Is that 6 time like that? No, I'm
Maybe
not.
kena letak kurungan kot.
Yes. Let's remove ni dulu. Let's see what happened. Remove that one first. Still error. What happened to 6? Do we have to put this like that or? Okay.
Betul-betul.
Okay. Maybe that's was okay. Let's verify.
and divide by 6 multiply with x square, sum of x square. Minus and all right, so we get 2.02 the okay slope, and B by right, B is sum of okay, sum of y multiply with sum of x square minus sum of x multiply with sum of x multiply with y, right, and then 6 multiply with minus 6 multiply with sum of x multiply with x. No, I think this is wrong. Sum of x square multiply with x square. Okay, so our interception x y is 1.132. So how do we verify this? Easy, we can draw. I take this and draw the chart. Okay, insert. You get the chart. So this is the distribution of x value versus y value. So this is the points. Okay, so you click here, add trend line. Because we are dealing with linear. No. So display equation on chart. All right. So as you can see here, the equation calculated by a linear equation by the Excel graph. So M is 2.0245. Okay, exactly. And the interception at Y is 1.13. Okay, so that's verify lah, the equation, okay, of the linear least square method to determine the M square and the interception. Okay. Okay, so I think let's cover that part. Let's see. And so I think it's I think for this part I finish. for uncertainty and probability. The rest basically like for example here, in the notes. Okay, so how to find the correlation coefficient. So correlation coefficient is basically for the trend line, showing you the quality of the perfect fit of the data. Okay, if it is close to 1 or negative 1 means that the data is perfectly linear. Okay, but less than that is not linear. So in our example before, coming back, so you can also estimate the R square. Go to the format trend line, and this R square value on the chart. So here R square is 0.9975, which means that the data is distributed very close to the linear trend line. So it's a good indicator or quality of the linear trend line in correlation with the data distribution. Okay. So the rest of the point of the data is for or the presentation slide is for you to refer lah. So I think I finished this part of uncertainty. So we stop.
Sorry,
Yes.
interrupt.
Yes.
We don't have the slide for 8D, the last one in e-learning.
8D. D.
Yes. This slide,
Okay. Are you MKEM or MEEM?
I'm MKEM.
Okay. Because this MKEM is not included in the evaluation, that's why I didn't put. But if you want to, okay lah, to be fair to everyone, I will include all the content in MKEM as well. I will do it later for MKEM. Okay, I will put for you to refer lah. This is knowledge. But in terms of evaluation, it will not include. I forgot to mention for MKEM. Literally, we have finished the syllabus. This slide and the next will not be included in your evaluation for MKEM. MKEM. But you are welcome to join and then to ni lah, basically to learn. So this next, I think we will resume at 2. So we will finish 2 more chapters, and these 2 more chapters will not be included in MKM. Also including this 8D, but I will share since you asked. But it's up to you. Meaning to say, for your test 2 and for your final, you don't have to study lah. Okay, but it may be useful for information or knowledge. Okay.
Okay, thank you, Doctor.
All right. So we stop here and we will resume at 2 p.m. or 15 past 2 lah. Okay. Thank you, everyone.